Okay, let's unpack this. When you picture Saturn, what comes to mind? For most of us, it's those breathtaking, iconic rings, right?
Absolutely. They're one of the most stunning sights in our solar system. Just captivating.
Shrouded in, well, a veil of cosmic mystery. Today, we're diving deep into Saturn, the ringed jewel of our cosmic neighborhood, to peel back those layers of beauty and uncover what truly lies beneath.
Yeah, we want to get beyond just the pretty pictures.
Exactly. We'll look at its long history, the groundbreaking missions that have explored it, and yes, even the tantalizing possibility of life lurking on its distant moons. And maybe the monumental challenges of humanity ever making a visit there.
Right. This deep dive is really about understanding not just what Saturn is on the surface, but why it's so uniquely important in our cosmic neighborhood.
So what's our mission today?
Well, our mission is to distill all of our sources, all the information we have, to give you a truly comprehensive, well-informed view of Saturn. From its basic composition and features right through to the ultimate question of habitability on its distant worlds.
Think of it as a shortcut, maybe.
Yeah, exactly. A shortcut to becoming well-versed in the incredible story of Saturn.
So let's start with Saturn's very identity. We often hear Saturn called a gas giant, right? Second largest planet in our solar system, just behind Jupiter.
That's correct.
But what does that truly mean for a world its size? And, what gives it that distinct, almost squished appearance? It doesn't look perfectly round.
No, it doesn't. And it's a fascinating combination of its mass and, crucially, its motion. Saturn is indeed a gas giant, which means it doesn't have a solid surface like Earth.
Right, no ground to stand on.
Not really, no. It's primarily made of hydrogen and helium swirling together in these immense atmospheric layers. And you're right about the shape. It's quite unique.
Oh, so?
Well, unlike Jupiter, which is more uniformly spherical, Saturn is noticeably flattened at its north and south poles, and because of that, it bulges wider around its equator.
Ah, okay, like it's being squashed a bit.
Exactly. If you look at the numbers, its equatorial diameter stretches an impressive 120,536 kilometers.
Wow.
While its polar diameter is significantly smaller at 108,728 kilometers.
So that difference is quite a lot, actually.
It's about a 9% difference, which is substantial for a planet.
A 9% difference is huge. And you mentioned motion. What causes that noticeable bulge? Is it just the gas?
No, it's the spin. That distinctive flattened shape is directly linked to Saturn's incredibly fast rotation.
How fast are we talking?
It spins once on its axis approximately every 10.8 Earth hours.
10.8 hours for something that massive.
Exactly. Imagine a planet that big turning that quickly. The centrifugal force generated by that rapid spin causes the material around its equator to bulge outwards while the poles get flattened.
Okay, I can picture that. It's like spinning a ball of pizza dough maybe flattens out.
That's a great analogy, actually. Yeah, it flattens at the top and bottom.
That makes so much sense. And beyond its shape, Saturn is known for its distinct pale gold hue. It's a beautiful color. What gives it that particular look? Is it all just hydrogen and helium doing that?
Well, hydrogen and helium are the main players, but it's primarily its atmospheric composition and the cloud structure that create the color.
Okay.
Saturn's atmosphere is about 75% molecular hydrogen and 25% helium, roughly, with only trace amounts of other elements like methane and water ice.
Just trace amounts.
Right. But within this gaseous envelope, particularly in Saturn's troposphere, there are three main cloud decks stacked on top of each other.
3 layers. What are they made of?
So the uppermost layer consists of ammonia clouds, and temperatures there plummet to a frigid negative 210 degrees Celsius, really cold.
Minus 200 C.
Wow. Beneath that, you find ammonia hydrosulfide clouds, slightly warmer, relatively speaking, at negative 70 degrees Celsius.
Still incredibly cold.
Oh, yes. And then at the very bottom of these main cloud decks are water clouds, H2O clouds, where the temperature actually reaches 0 degrees Celsius.
Water clouds at 0 degrees Celsius. That's, still freezing by Earth standards, but almost balmy compared to the extreme cold above. So how do all these layers mix together to create that pale gold color we see?
It's a fascinating interplay, really. Deep within the atmosphere, there are clouds of red hydrogen.
Red hydrogen?
Yeah. However, these are largely obscured from our view by the white ammonia clouds that are closer to the outer edge of the atmosphere. They basically envelop the entire planet.
Ah, okay. So the white clouds cover up the red ones.
Pretty much. And these ammonia clouds get their white appearance from exposure to the sun's ultraviolet radiation. So it's the blending of these obscure deep reds and the prominent whites that gives Saturn its overall pale gold appearance.
That's really cool. It's like layers of paint mixing.
In a way, yes. And this atmospheric activity also drives some of the fastest winds in the solar system, second only to Neptune's.
How fast are we talking?
They can reach incredible speeds of up to 35,500 kilometers per hour.
35,000 kilometers per hour. That's mind-blowing. It's a truly dynamic and colorful atmosphere then.
Extremely dynamic.
Speaking of dynamic atmospheres, we absolutely have to talk about one of Saturn's most curious and, frankly, captivating features.
Yeah.
That enormous spinning hexagon in the clouds at its north pole.
Ah, yes. The hexagon.
This thing has fascinated scientists and, the public alike since we first glimpsed it back in the 1980s with Voyager.
Mm.
What makes it so unique compared to anything we see on Earth? Our weather doesn't do that.
It truly is a marvel. And you're right, there's nothing like it here. This hexagon is absolutely massive. Its diameter is more than twice the width of Earth.
Twice the Earth.
And its sides and angles are remarkably symmetrical. It forms this really ordered geometric pattern that spins like a giant cosmic top right there at the pole.
It looks so artificial almost.
It does. For us, accustomed to the weather patterns on Earth where jet streams slither and meander with no discernible pattern or symmetry.
Yeah, they just wiggle around.
Exactly. And weather systems just swirl and twirl throughout the globe.
This geometric cloud pattern on Saturn seems, well, curious. Or even alien, as you said. It really challenges our intuitive understanding of how atmospheres behave.
It feels completely unnatural to us. But obviously it's natural.
Oh, absolutely. Yet, both Saturn and Earth's atmospheres follow the same natural laws of physics and fluid dynamics.
Mm-hmm.
It's just that the different conditions, the rotation speed, the composition, the temperature gradients produce these wildly different results.
Right. And the Cassini probe, which orbited Saturn for over a decade, gave us such incredible views and data. It provided some surprising answers about this hexagon, didn't it?
It did. Cassini gave us unprecedented detail, confirming it's a long-lived jet stream feature, essentially.
Yeah.
What's even more intriguing is that not all the questions are resolved. We still don't fully understand exactly why it maintains such a perfect hexagonal shape.
Which honestly just heightens the mystery even more. It's fantastic.
It certainly does. And, it ties into how Saturn even got its name in the first place. It's steeped in history and mythology. Oh yeah, where does the name come from?
It's named after the Roman god Saturn. He is the Roman equivalent of the Greek god Cronus.
Cronus, the Titan.
That's the one. In Greek mythology, Cronus was the powerful and often fearsome leader of the Titans, a primordial race of deities.
And he had a bit of a reputation, didn't he?
He did. He was known for, among other things, devouring his own children to prevent a prophecy that they would eventually overthrow him. Grim stuff.
Grim stuff indeed. But this connects beautifully to some of the earliest observations of Saturn, right? With Galileo.
Exactly. When Galileo first observed Saturn through his pretty primitive telescope back in 1610.
Must have been blurry.
Oh, incredibly so. He couldn't quite make out the rings as solid structures or even as rings at all. His early limited observations led him to describe Saturn as having 3 bodies side by side, or even more colorfully, as having ears.
Saturn's ears. I love that.
It's a great image. Then, in 1612, something really confusing happened from his perspective. Earth passed through the plane of Saturn's rings.
So they disappeared.
They became completely invisible from our perspective because they're so thin edge-on. And this really puzzled Galileo.
I bet. What did he think?
He famously remarked, "I do not know what to say in a case so surprising, so unlooked for, and so novel." He even mused, "Has Saturn swallowed his children?"
Whoa, directly referencing the myth.
Directly referencing the myth of Cronus devouring his offspring. His confusion was further compounded when, to his astonishment, the rings reappeared in 1613.
That must have blown his mind.
Completely. It's a wonderful anecdote, isn't it? It bridges the early struggles of scientific observation with ancient mythology, highlighting the initial mystery surrounding this ringed world.
What a fantastic connection between ancient myth and early astronomy. But, it wasn't long before better technology started to resolve some of those initial mysteries, thankfully.
Right. Progress was relatively quick after that. Just a few decades later, in 1655, the Dutch astronomer Cassini-Huygens used a much more powerful telescope.
And he saw them properly.
He had that breakthrough moment, yes. He correctly identified those structures as rings, a continuous disk surrounding the planet.
The big leap.
And that wasn't his only discovery related to Saturn. Huygens also discovered Saturn's largest moon, Titan, in the same period. significantly advancing our understanding of the planet and its system.
So Huygens gave us rings and Titan. Huge contributions.
Indeed, Huygens' work was a major leap forward, transforming those puzzling ears into the distinct ring system we recognize today. Then, later in the late 17th century, the Italian-French astronomer Giovanni Domenico Cassini—
Cassini. The name sounds familiar.
the very same. He continued to build on these discoveries. Between 1671 and 1684, Cassini made several significant findings himself.
Like what?
He identified 4 new moons orbiting Saturn: Iapetus, Rhea, Tethys, and Dione, adding to the growing family.
Wow, 4 more moons.
And crucially, he also discovered a prominent gap within Saturn's rings, a dark division.
That must be the Cassini division.
Precisely. The famous Cassini division, which is a clear separation we can see between the A and B rings. These early observations, while obviously limited by the technology of the time, really laid the essential groundwork for all the future robotic exploration that would follow centuries later.
Incredible history. And that future really began, I suppose, in 1979 with Pioneer 11. That was the first visitor from Earth to the Saturnian system, wasn't it?
It was the first flyby, yes. Pioneer 11 truly set the stage, giving us our first real close-up look.
How close did it get?
It made a very close approach, flying within 20,000 kilometers above Saturn's cloud tops, really skimming the planet.
Wow. Beyond just getting pictures, what was the most surprising scientific revelation from Pioneer 11's flyby? Did it challenge any existing ideas?
It really did. Pioneer 11's flyby was instrumental in showing us just how dynamic the system was. One of its key revelations was the first discovery of the thin F-ring.
The F-ring.
Yes, a very narrow, complex ring just outside the main A-ring. But perhaps even more surprising was its observation about the dark gaps within the rings, like the Cassini division.
What about them?
When Pioneer 11 viewed these gaps looking back towards the sun, they surprisingly appeared bright, not dark.
Right. How could a gap be bright?
Exactly. This indicated that they weren't entirely empty, as people had assumed. They actually contained diffuse material, very fine particles that scattered some light forward.
Ah, forward scattering. Okay.
It immediately suggested the rings were far more intricate and dynamic than just a simple collection of distinct, solid bands with empty spaces.
That's a really important finding. Anything else, Major?
Additionally, Pioneer 11 provided our first measurements of the temperature of Titan, giving us an early hint about its unique, cold, and thick atmosphere.
So Pioneer 11 really opened the door. That's a powerful way to think about it, that those empty spaces weren't empty at all. But the real grand tour, the big show, came with the twin Voyager missions, right?
Oh, absolutely. Voyager 1 and Voyager 2, launched just weeks apart in 1977, were designed as this incredible pair of spacecraft to explore all the outer planets: Jupiter, Saturn, Uranus, and Neptune.
The grand tour, it still sounds amazing.
It was, and remarkably, Voyager 1 continues its journey to this day. It holds the record as the most distant human-made object from Earth, now well into interstellar space.
Just incredible. So Voyager 1's encounter with Saturn must have been a highlight.
It definitely was. It offered a wealth of new insights. Its closest approach to Saturn itself was on November 12, 1980, at a distance of about 184,300 kilometers.
Closer than Pioneer.
No, Pioneer was closer to Saturn itself, but Voyager 1 also had a very close flyby of Titan on the same day.
How close to Titan?
It got within a mere 6,490 kilometers of Titan. Really close. This allowed for detailed atmospheric studies that confirmed it had this thick, hazy, nitrogen-rich atmosphere.
And what about the other moons? Did Voyager look at Enceladus?
Yes, what's particularly fascinating is that Voyager 1 also performed a flyby of Enceladus. It wasn't super close, about 202,000 kilometers away.
What did it see?
Well, the images it acquired, while pretty low in resolution compared to Cassini,
Sure.
they revealed a highly reflective surface. Very bright. And crucially, it was notably devoid of impact craters in the areas it saw well.
No craters on a small moon. That usually means.
Exactly. It suggested a surprisingly youthful surface. Something must have been resurfacing it relatively recently, geologically speaking.
So even with those early kind of blurry images, scientists were already getting hints that Enceladus was special. What did they infer from that smooth, reflective surface?
Precisely. In fact, based on these early Voyager observations, scientists proposed a really groundbreaking idea at the time.
Which was?
That Saturn's E-ring this broad, tenuous ring that Enceladus orbits within, actually consisted of particles vented directly from Enceladus's surface.
Wow, so they suspected plumes even back then.
They suspected some kind of venting mechanism, yes. This was a revolutionary concept for a small, icy moon. It suggested ongoing geological activity where none was really expected.
That's amazing foresight.
It really was. And a fascinating postscript to that is a 2017 reprocessing of some of those Voyager departure images using modern techniques.
Yeah.
They actually revealed what scientists are calling a possible recovery image of Enceladus's plumes. A faint hint, maybe, of what Cassini would later confirm in spectacular fashion.
Incredible, like finding an old photo that suddenly makes sense.
Exactly. And while Voyager 1's cameras were deactivated way back in 1990 to conserve energy for its long journey,
It's still going.
it's still going, yes. Its mission continues to this day, sending back data about the environment in interstellar space. A true pioneer.
Incredible legacy. So Voyager gave us a tantalizing taste, but then came Cassini-Huygens, which truly fundamentally revolutionized our understanding of the entire Saturnian system.
Absolutely. Cassini-Huygens was the game changer.
What was the genesis of this monumental mission? It was a huge collaboration, wasn't it? And why was it such a massive undertaking?
It was indeed a joint flagship mission, a monumental collaboration between NASA and the European Space Agency, ESA.
NASA and ESA.
Its origins actually trace back to the early 1980s, believe it or not, but it faced a difficult physical climate, as NASA's Jet Propulsion Laboratory noted back then. Budgets were tight.
The usual story.
Yeah. So that pushed its official approval back to 1989. It was finally launched aboard a powerful Titan IVB Centaur rocket on October 15th, 1997.
Okay, 97 launch. And it took a while to get there.
It did. After a long and complex journey, it finally arrived at Saturn on July 1st, 2004. Marking the beginning of 13 years of orbital study around the ringed planet.
13 years?
It was a huge undertaking because of, well, the immense distances involved, obviously, and the need to carry this unprecedented array of sophisticated scientific instruments. It was a flagship mission for a reason.
That's a long journey just to get there. How did it manage the trip? Did it just fly straight there?
Oh, no, not at all. The voyage to Saturn was an intricate ballet of orbital mechanics. It employed what's called an Earth Gravity Assist, or EGA, trajectory.
Gravity assists, using planets like slingshots.
Exactly. This involved multiple planetary flybys to gain momentum and shape its path. Cassini performed 2 flybys of Venus first.
2 of Venus.
Yep, then swung back past Earth for another boost. It even made a flyby of the asteroid 2685 Masursky in January 2000.
An asteroid 2. Bonus science.
Right, where its diameter was estimated to be between 15 and 20 kilometers. That was a neat extra. The journey culminated with a big Jupiter flyby in December 2000.
Using Jupiter's huge gravity.
Precisely, during which Cassini also made some interesting observations of Jupiter's rings, actually, noting that the way light scattered indicated they were composed of irregularly shaped particles, likely originating from micrometeorite impacts on Jupiter's small inner moons.
So it wasn't just a mission to Saturn, but a grand tour through the inner and middle solar system on the way.
You could definitely say that. It gathered science all along the route.
And the impact once it got there sounds like it was truly revolutionary. I remember reading Jim Green, who was NASA's Planetary Science Division Director, describing Cassini-Huygens as a mission of firsts.
That's a perfect description.
He said it truly revolutionized human understanding of the Saturn system, including its moons and rings, and importantly, expanded our understanding of where life might potentially be found in the solar system.
Indeed, the mission's success was truly beyond expectations. It delivered on almost every front, and then some.
And Cassini's incredible journey finally came to an intentional end, didn't it? In a pretty dramatic way.
Yes, in the grand finale on September 15th, 2017, the spacecraft was deliberately plunged into Saturn's upper atmosphere.
Why did they do that? Why not just leave it orbiting?
It was a carefully planned maneuver driven by planetary protection protocols. The goal was to prevent any risk, however small, of the spacecraft eventually crashing into and contaminating Saturn's moons, particularly those like Enceladus or maybe even Titan, which might have offered habitable environments.
So to protect potential native life from Earth germs.
Exactly. It ensured that if life were found there in the future, we could be confident it was native to that moon, not a stowaway from Earth carried by Cassini. A responsible end to the mission.
That makes sense. A noble sacrifice. This brings us to a truly fascinating point about Cassini. It was absolutely packed with an incredible array of instruments, each one a testament to scientific ingenuity.
It really was a flying laboratory.
This wasn't just a collection of sensors. It felt like a testament to how human ingenuity built this remote sense of the universe, allowing us to virtually touch and taste a world millions and millions of miles away. Can you tell us more about the power of these instruments? What could they actually do?
It's a crucial insight, and the suite of instruments on Cassini truly was groundbreaking. Let's start with its eyes. Its imaging systems, particularly the Imaging Science Subsystem, or ISS.
The cameras.
Right. These were Cassini's primary camera eyes. They captured hundreds of thousands of images across visible light, infrared, and ultraviolet light, allowing us to see Saturn, its rings, and its moons in absolutely unprecedented detail. This gave us our first truly clear and continuous visual story of the whole system.
So, stunning pictures. But to understand what those images were telling us, Cassini also had powerful spectrometers, right? To analyze the light.
Exactly. Spectrometers break down light into its component colors or wavelengths, which tells you what things are made of. The Composite Infrared Spectrometer, CIRS, measured infrared radiation, which is essentially heat. This allowed it to determine temperatures, thermal properties, and compositions of atmospheres, rings, and surfaces throughout the Saturn system. It effectively mapped Saturn's atmosphere in 3 dimensions, revealing its layers and dynamics.
3D maps of the atmosphere.
Yeah. Similarly, the ultraviolet imaging spectrograph, UVIS, captured images in ultraviolet light. And it was UVIS that crucially confirmed the spectacular water vapor plumes erupting from Enceladus' south pole.
Ah, UVIS saw the plumes.
Confirmed them definitively, yes. So these instruments allowed us to understand not just what things look like, but what they were made of and how they behave thermally and chemically.
Amazing. Beyond just light, Cassini also had radar capabilities, didn't it, for probing hidden surfaces, like on Titan?
Absolutely. Titan's haze was a major obstacle. The radar instrument was powerful enough to penetrate Titan's notoriously thick, hazy atmosphere.
Gotta do that.
It bounced radar waves off the moon's surface. By timing how long the echoes took to return and measuring their strength, it could map surface features like rivers, lakes, dunes, and mountains, and even determine the height of mountains and the depth of canyons. It essentially gave us our first clear, topographic view of a world shrouded in smog.
Seeing through the haze. And then, for the tiny bits and pieces floating around Saturn, the dust and gas.
For that, Cassini had in situ particle detectors, instruments that directly sampled the environment around the spacecraft, like the Cosmic Dust Analyzer, or CDA, which measured the size, speed, direction, and even the chemical elements of tiny dust grains near Saturn, and the Ion and Neutral Mass Spectrometer, INMS, which analyzed the composition of both charged particles, ions, and neutral atoms and molecules. This was crucial near Titan and Saturn to understand their atmospheres, and also essential for analyzing the material in the rings and, significantly, in the plumes of Enceladus. These instruments literally tasted the environment.
So Cassini could see, sense temperature, measure composition with light, map surfaces with radar, and even feel and taste its surroundings with these particle detectors. Incredible sensory package. What about invisible forces like magnetic fields and the charged environment, the plasma?
Yep, it had instruments for that too, covered all the bases. It carried magnetic field and plasma instruments. The dual technique magnetometer, MAG, measured the strength and direction of Saturn's magnetic field with high precision. This allowed scientists to infer properties of its deep interior, potentially its molten core, and model its magnetosphere, the giant magnetic bubble surrounding the planet.
Protecting it from solar wind.
Exactly. Then the magnetospheric imaging instrument, MEM, actually imaged the energetic charged particles trapped in Saturn's magnetic field, helping us understand the dynamics of the magnetosphere, how particles circulate and get energized, and the radio and plasma wave science instrument, RPWS. Listened for radio waves and plasma waves. It received and measured radio signals naturally produced by the planet, like lightning discharges from within Saturn's atmosphere and waves generated in the plasma and magnetic field. It studied Saturn's magnetic field, its ionosphere, the plasma environment, and even detected that lightning.
Listening to Saturn's static and lightning.
Yeah.
Wow. Did all the instruments work perfectly for the whole mission?
Almost. There was one unfortunate issue. One of the plasma instruments, the Cassini Plasma Spectrometer, or CAPS, did unfortunately suffer an electrical short circuit partway through the mission in 2011-2012, and it had to be permanently shut down to protect the rest of the spacecraft.
Oh, that's a shame. But still, an incredible suite.
Even with that setback, the mission continued to gather immense amounts of crucial data from all the other instruments. And what's perhaps even more amazing is how the Cassini team went beyond the original design specifications for these instruments.
How so?
They showed incredible ingenuity and adaptability, finding new ways to use the instruments and even the engineering systems of the spacecraft that their designers hadn't even foreseen.
That raises a really important question for future missions, doesn't it? How can we design spacecraft with that kind of inherent adaptability built in from the very start? Can you give some examples of Cassini's repurposing?
Absolutely, it's a key lesson. For instance, they repurposed the radar instrument, which is primarily designed to map Titan's solid surface features, to actually plumb the depths of Titan's vast liquid methane and ethane seas, measuring how deep they were.
Using radar to measure sea depth on another world.
Exactly. They also used instruments specifically designed to sample Titan's upper atmosphere, like INMS, to fly through and directly taste the plume of Enceladus, yielding that incredible data about its composition, water, salt, organics, hydrogen.
Instruments meant for Titan, used on Enceladus. Clever.
Very clever. And the Deep Space Network's highly accurate frequency reference on Earth was even used to fill in for a lost onboard frequency reference, allowing crucial radio science experiments to continue.
So ground control helped out too.
It was a huge team effort. The attitude control and navigation teams joined with the instrument teams to develop a consolidated model of Titan's atmosphere using data from multiple sources. And Cassini's ultimate act, before its grand finale plunge, was to once again repurpose its instruments that had sniffed Titan's atmosphere and Enceladus's plume, this time sampling Saturn's own upper atmosphere itself as it dived between the planet and the rings, literally tasting the giant planet.
Wow, from tasting moons to tasting the planet itself, what a final act.
It truly was a testament to human ingenuity, collaboration, and making the absolute most of a precious resource millions of miles away.
That level of repurposing is just mind-blowing. It really maximizes the scientific return of these incredibly expensive and complex missions. And when you think about Saturn, after it's, the planet itself, the next thing that comes to mind always is its rings. They are just a cosmic masterpiece. The scale and scope of them are just vast.
They truly are spectacular. Saturn's rings are not only the largest and brightest of the 4 ring systems surrounding the giant planets in our solar system.
Jupiter, Uranus, Neptune have rings too, but fainter.
Much fainter, yes. Saturns are in a class of their own. They also contain at least as much mass as Saturn's mid-sized moon Mimas, so a significant amount of material.
As much as a moon.
To illustrate their immense size, if you stretch them out, they are almost as wide as the distance between the Earth and our moon.
Earth to the moon distance. That's incredible.
But here's the key insight, the thing people often get wrong. Despite looking like solid discs from a distance, like a vinyl record.
Yeah, that's what they look like.
They're not a solid track at all, not even close. Instead, they're made of literally millions, probably billions of individual chunks of ice. Mostly water ice.
Chunks of ice, how big?
They range hugely in size. From particles as tiny as dust, like smoke particles, up to pieces as large as buses, or even small houses, all orbiting Saturn independently like tiny moonlets.
So it's a giant, dynamic cosmic debris field made of ice.
That's a perfect description. A giant, dynamic cosmic debris field.
That's incredible, a giant cosmic debris field. So what exactly is the structure of this massive ring system? You hear about the A ring, B ring, C ring. Are they just 7 simple, distinct bands, like in the old diagrams?
Oh, it's far, far more complex and intricate than those simple diagrams suggest. We generally talk about the main, brighter divisions first. The A, B, and C rings. Those are the ones most easily seen from Earth.
A, B, C. Okay.
Closest to Saturn is the innermost D ring, which is very faint and less dense. Then moving outward from the bright A ring, there's the narrow, fascinating F ring.
The one Pioneer 11 discovered.
That's the one. Discovered by Pioneer 11 in 1979. It's just outside the A ring, and it's known for its bizarre braided structure. Beyond that is the G ring, another narrow, faint ring. And it was actually in an empty area between the F and G rings that Cassini performed its orbital insertion burn, entering the Saturn system safely.
Wow, threading the needle.
Pretty much. And then further out still, there's the very broad and tenuous E ring, which is huge, but very diffuse and notably centered on the orbit of the moon Enceladus.
Ah, the E ring is linked to Enceladus. That makes sense with the plumes.
Exactly. The E ring is thought to be composed primarily of icy particles ejected from Enceladus's geysers.
So what this all means is the rings are far more complex than just Pretty cosmic jewelry. They're this incredibly dynamic system with a huge variety of observed features. You mentioned gaps with embedded moons, ringlets, waves, wakes, even wiggles. What does all that tell us?
It tells us the rings are constantly interacting with Saturn's moons and with each other. They're incredibly dynamic and continually evolving structures. The particles within these rings aren't just flowing randomly. They are mainly aggregates of smaller particles, clumping together transiently into elongated clumps, maybe tens of meters in size.
Lumps of ice particles.
And the small moons orbiting near and even within the rings are intimately involved in creating and sculpting their intricate structure. They act like gravitational shepherds.
How do they do that?
For example, density waves, these beautiful spiral patterns you see in the ring, are excited by gravitational resonances with nearby moons like Janus or Mimas. The moon's gravity rhythmically tugs on the ring particles, creating these waves like ripples in a pond.
Like gravitational ripples.
Exactly. Then you have small embedded moons, sometimes called moonlets, that orbit right within gaps in the rings. They create what are called satellite wakes, disturbances trailing behind them, and they perturb the edges of the gaps that they clear within the rings.
Keeping the gaps open.
Right. There are even these fascinating features called propeller-shaped structures.
Propellers. In the rings.
Yeah, they look like tiny airplane propellers embedded in the ring plane. They're thought to be caused by objects maybe a few hundred meters across, not quite large enough to clear a full circular gap like a proper moon, but still massive enough to gravitationally disturb the ring material around them, creating these propeller-like wakes. They might be an intermediate stage in moon formation or maybe remnants of disrupted bodies.
Wow. It sounds like a cosmic ballet almost, with the moons acting as choreographers, constantly shaping and reshaping the ring system.
It is a beautiful analogy and quite accurate. It's a constant dance of gravity. For instance, particles in the dense A and B rings don't just orbit smoothly. They cluster together into temporary strands or self-gravity wakes that are maybe tens of meters across and hundreds of meters long.
Wakes caused by their own gravity.
Yes, these clumps form due to the particles' own weak mutual gravity trying to pull them together. But they are constantly being sheared apart by Saturn's gravity. Remember how inner particles orbit faster than outer ones?
Right, the Keplerian shear.
That shear stretches any clumps out, preventing them from collapsing into solid moons within the main rings. So these wakes are in this dynamic equilibrium between gravitational accretion trying to build things up and tidal shear tearing them down.
A constant construction and demolition process.
Exactly. And in the peaks of those strong density waves we talked about, particles pile together even more densely in what you could describe as a cosmic traffic jam. This can result in kilometer-long strands that might just be larger versions of these self-gravity wakes.
Kilometers long.
Yeah. And the F ring, that narrow, chaotic one, it's a particularly dramatic showcase of accretion and disruption. We see clumps forming within it, maybe kilometer-sized bodies, but then they get disrupted, pulled apart, often due to encounters with the nearby shepherd moon Prometheus, which orbits just inside it and gravitational perturbs it constantly.
So Prometheus is stirring up the F ring.
Constantly. It leaves channels and knots and braids in its wake. This constant interaction means the rings are dynamic and continually evolving on all sorts of timescales, from days to potentially tens or hundreds of millions of years. Each new observation, especially from Cassini, revealed even more intricate structure and activity.
It's just endlessly complex. And speaking of complexity, Cassini data showed something else truly amazing. The rings aren't just chunks of ice and rock. They have their own atmosphere, separate from the planets. That's a profound revelation, isn't it?
It is absolutely mind-boggling when you first hear it. But yes, the rings generate their own tenuous atmosphere.
How is that possible? What's it made of?
It primarily contains molecular oxygen, O2, and hydrogen gas, H2. The oxygen forms when the sun's ultraviolet light strikes the water ice, H2O, in the rings. The UV light breaks apart the water molecules.
Splitting water into hydrogen and oxygen.
Right. Some hydrogen escapes, some reacts further. Other chemical reactions involving UV light and water molecules also produce hydrogen gas. And interestingly, the Hubble Space Telescope also discovered a thin atmosphere primarily composed of hydroxide around the rings.
Oxygen, hydrogen, hydroxide. Wow. And what's this about ring rain? That sounds poetic.
It does sound poetic, but it's a real process. Cassini's instruments detected material, primarily water ions, but likely including other ring particles, being pulled inwards along Saturn's magnetic field lines from the rings and falling into the planet's upper atmosphere.
So the rings are literally raining down onto the planet. That's wild.
It is wild. It's a process that seems to be happening continuously, and over very long timescales, it will eventually lead Saturn to lose its rings entirely. The
Yeah.
planet is slowly consuming them.
Whoa. So Saturn's most iconic feature is temporary. But that process must take forever, right? It makes you wonder what future generations, maybe millions of years from now, might see when they gaze at Saturn.
It will indeed take a very long time by human standards, probably hundreds of millions of years, maybe less, for complete dissipation based on current estimates of the infall rate. So it's not something we'll witness in our lifetime, or even humanity's lifetime so far.
Okay, good. Like the rings.
Me too. But it's still impressive to think that in the distant future, there could be a Saturn without rings. Though actually, we get a preview of this phenomenon much more often than you might think, just due to geometry.
How so?
Because of Saturn's axial tilt, just like Earth is tilted on its axis, causing seasons.
Yeah, 23.5 degrees for us.
Saturn's axis is tilted by a similar amount, 26.7 degrees relative to its orbit around the Sun. And this tilt causes us to see widely varying views of its rings from Earth as both planets move through their orbits over the years.
Oh, right. So sometimes we see them wide open, showing their full glory, and other times they appear edge-on. That dynamic view must be quite a sight for astronomers over time.
Exactly. Earth actually passes through the plane of the rings about every 13 to 15 years, roughly every half Saturn year, since Saturn takes about 29.5 Earth years to orbit the Sun.
Ring plane crossings.
Yes. During these ring plane crossings, the rings can appear to vanish completely from our view for a short time because they are so incredibly thin compared to their width, maybe only tens of meters thick in most places.
So they just disappear.
Visually from Earth telescopes, yes. For example, we're actually heading towards one soon. A preview of Saturn's globe, seemingly without its rings, will be available to us starting around March 2025 during one of these crossings.
March 2025. That's coming up. When's the next time after that?
The next notable crossing opportunities after 2025 will occur around October 15th, 2038, then again on April 1st, 2039, and July 9, 2039.
Okay, mark the calendars.
It's a fascinating natural phenomenon that reminds us of the dynamic nature of this system and how our perspective changes as Earth and Saturn dance around the Sun.
Absolutely fascinating. Okay, from the rings, let's pivot to Saturn's incredible collection of moons. You mentioned Cassini discovering more, and the numbers are just staggering. This planet has the most known moons of any planet in our solar system. What's the latest count?
The number keeps going up as we find smaller ones. Currently, there are 274 known moons with stable and confirmed orbits around Saturn.
274. That's incredible.
It really is a moon-rich system. And Cassini truly revealed a bewildering variety among them. It showed us that each one is essentially a unique world in its own right, not just boring rocks.
What does this bewildering variety tell us about? Maybe cosmic diversity or how planetary systems form?
Well, what this bewildering variety tells us isn't just about cosmic diversity in general, but specifically how subtle differences in formation, location, composition, impacts, and gravitational interactions within the Saturnian system itself can sculpt entirely unique worlds. Each moon is like a little universe in miniature, with its own story.
Can you give some examples of this variety? You mentioned some weird shapes earlier.
Oh yeah, the shapes alone are amazing. You have Iapetus, for example, which is famous for its noticeable giant ridge running right around its equator.
The equatorial ridge. So strange.
And its perplexing two-tone color pattern. One whole hemisphere is incredibly bright ice, the other is coated in very dark material. Then there's Mimas, instantly recognizable for its absolutely enormous impact crater, Herschel, making it look startlingly like the Death Star from Star Wars.
The Death Star moon. Yep.
Then Hyperion looks strangely like a giant tumbling sponge or coral with deep, weirdly shaped craters. Atlas, one of the inner moons, looks like a flying saucer or a UFO because it has this smooth equatorial ridge made of accumulated ring material.
A flying saucer moon.
Prometheus, one of the F-ring shepherds, is just a lumpy potato-shaped moon. And maybe the most bizarre, Pan, which orbits inside the Eck gap in the I-ring, has accumulated ring material around its equator too, making it look exactly like a piece of cosmic ravioli.
Ravioli. That's amazing. So these are not just plain, round rocks. They're truly unique characters in the Saturnian play.
Characters is a good way to put it. This sheer variety underscores the complex gravitational dance within the Saturnian system and how even small bodies can have dramatic individual histories shaped by their environment.
But among all these hundreds of moons, two really stand out for their incredible scientific interest and potentially their implications for life. Titan and Enceladus.
Absolutely. They are the superstars.
Let's start with Titan, Saturn's giant moon. What makes it so special that it's often compared to an early Earth, despite being so different?
Titan is indeed a giant. It's Saturn's largest moon by far. It's so big that it's actually larger than the planet Mercury.
Bigger than a planet?
Yep, making it the second largest moon in the entire solar system, only surpassed by Jupiter's Ganymede. But what truly sets Titan apart, the reason for the Earth comparison, is that it's the only world we know of, other than our own Earth, that has stable bodies of liquid on its surface.
Liquid on the surface, but not water, right?
Correct. Instead of water, these are vast lakes and even seas composed of liquid hydrocarbons, primarily methane and ethane.
Liquid methane seas, that's wild.
It is, and it seems to have a cycle similar to Earth's water cycle, but with methane. Methane evaporates, forms clouds, rains down, flows in rivers, and collects in these lakes and seas. This makes it eerily similar to Earth's hydrological cycle, just with completely different chemistry operating at incredibly cold temperatures, around -180°C.
A truly alien landscape, yet surprisingly familiar in its processes. And it also has that notorious atmosphere, right? The thick haze.
Yes. Titan is completely enveloped by a thick, dense atmosphere. It's composed primarily of nitrogen, just like Earth's atmosphere.
Well, mostly nitrogen. Interesting.
About 95% nitrogen, yes, but the rest is mostly methane with traces of other hydrocarbons. And complex photochemical reactions high up in the atmosphere, driven by sunlight and Saturn's magnetosphere, create this thick organic haze like smog.
The orange smog.
Exactly. This haze was so thick that it completely obscured Titan's surface from view for centuries, until Cassini's radar and infrared instruments were finally able to penetrate it and map the surface.
And how thick is that atmosphere compared to Earth's?
It's remarkably substantial. The surface pressure is about 1.5 times that of Earth's, and the atmosphere itself is much more extended. Measured by density, you could say it's about 4 times denser or thicker overall than Earth's atmosphere.
Wow. And what did Cassini find beneath that haze? What's the surface like?
Despite its extreme cryogenic temperatures, Titan's surface appears geologically young and generally quite smooth in many areas, with surprisingly few large impact craters visible. This suggests ongoing geological processes are resurfacing it.
Like erosion or volcanism?
Both, possibly. Cassini discovered vast fields of dunes, likely made of solid organic particles shaped by winds. It found evidence of river channels and shorelines around the lakes. And, intriguingly, it found mountains, some reaching up to 1 kilometer in height, possibly formed by tectonic activity. There's also evidence of possible cryovolcanoes.
Cryovolcanoes,
Yeah.
ice volcanoes.
Yes, volcanoes that would erupt slushy water mixed with ammonia from Titan's interior onto the surface, rather than molten rock. This hints at internal heat and ongoing geological activity, constantly reshaping the landscape.
What's fascinating here is how Titan, despite its extreme conditions, the liquid methane, the cryogenic temperatures, the smoggy atmosphere, share some surprising geological and atmospheric parallels with Earth, like dunes, rivers, lakes, nitrogen atmosphere.
Exactly. It's truly a world of immense scientific interest for understanding planetary evolution and the potential diversity of planetary processes. It's like Earth in a deep freeze with different chemicals.
Okay, now let's talk about the other superstar moon, Enceladus, the little icy geyser world. How did Cassini stumble upon its most dramatic feature, those plumes? Was expected?
Enceladus has proven to be an absolute marvel, and while the Voyager data hinted at activity, the scale of what Cassini found was stunning. Cassini made the spectacular discovery of these enormous plumes of water vapor and ice particles shooting hundreds of kilometers into space from cracks and fissures on its icy surface.
Geysers on an icy moon.
Giant geysers, yeah. Particularly concentrated near the South Pole, emanating from 4 distinct parallel fractures dubbed the tiger stripes. This was a game changer, absolutely unexpected in its scale and composition.
And what did Cassini find in those plumes? Was it just water?
No, that's what made it so exciting. Analysis of the plume material, using instruments like INMS and CDA that flew right through them.
Tasting the plumes again?
Literally tasting them. It revealed they contain not just water vapor and ice grains, but also significant amounts of salt, sodium chloride, like table salt mixed with the water.
Salted water. Like an ocean.
Precisely. That was the huge implication. They also found grains of silica-rich sand, tiny nanoparticles of rock, plus nitrogen, likely in the form of ammonia dissolved in the water, and crucially, a variety of complex organic molecules.
Organic molecules, what kind?
These include simple hydrocarbons such as methane, CH4, propane, C3H8, acetylene, C2H2, and even formaldehyde, CH2O. All carbon-bearing molecules, the fundamental building blocks for life as we know it.
So not just water, but a whole cocktail of interesting ingredients. And this directly led to the confirmation of an underground ocean, right? How did they confirm that?
That's right. The salty composition, the presence of silica nanoparticles, which suggested hot water interacting with rock, and measurements of Enceladus's tiny wobble as it orbited Saturn all pointed strongly towards a subsurface ocean. The confirmation came in 2015 based on detailed analysis of Cassini's gravity measurements during close flybys. These showed that the moon's icy outer shell wasn't frozen solid to the core, but was decoupled, slipping over a global layer of liquid water beneath it. A global subsurface ocean.
A global ocean hidden under the ice. How is it kept liquid on such a small, cold moon?
That's the amazing part. It's kept liquid by the powerful tidal forces exerted by Saturn. As Enceladus orbits Saturn, Saturn's gravity constantly stretches and squeezes the little moon, especially because its orbit isn't perfectly circular.
Tidal heat.
Exactly, tidal heating. This constant flexing generates friction and heat within Enceladus's interior, much like repeatedly bending a paperclip warms it up. This internal heat is sufficient to maintain a liquid ocean beneath the ice shell.
And this internal heating implies more, doesn't it? Like maybe hydrothermal vents.
Precisely. The presence of those silica nanoparticles, which typically form in hot water interacting with rock at temperatures above 90 degrees Celsius, strongly indicates that hydrothermal activity, like the hydrothermal vents we find on Earth's ocean floor, may be at work within Enceladus's ocean, down on the seafloor.
Hotspots on the ocean floor.
And these vents are crucial because they represent a source of chemical energy and potentially nutrients, places where life thrives in the deep, dark oceans on Earth.
What about the core itself? Is it just rock?
Models based on Cassini's gravity data and the plume composition suggest that Enceladus's large rocky core isn't a solid, impermeable ball. It's likely highly porous, like a sponge.
A porous core. Why is that important?
It allows water from the ocean to percolate deep into the core, interacting extensively with the rock. This flow would facilitate the transfer of heat generated by tidal forces within the core and, crucially, leach chemicals and minerals from the rock into the ocean. It provides a mechanism for supplying crucial energy sources and nutrients from the rock into the water, potentially feeding any life that might exist there, much like hydrothermal systems operate on Earth.
This is just incredible. A small icy moon with a global saltwater ocean, organics, and likely hydrothermal vents powered by tidal heating. This brings us squarely to the ultimate question. Is there life beyond Earth, specifically in the Saturnian system? Enceladus is looking like a seriously strong candidate for habitability. What makes it such a compelling target, summing it all up?
It truly is one of the most compelling places in the solar system to search for present-day life beyond Earth. You've got the essential ingredients as confirmed by Cassini: liquid water, a global ocean, essential chemical elements, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, often called CH and OPS, and critically, sources of energy.
Water, chemicals, energy. The trifecta for life.
Exactly. The likely hydrothermal activity provides both heat and chemical energy. And adding to that energy component, the detection of molecular hydrogen, H2, dissolved in the ocean water and present in the plumes is incredibly significant.
Why is molecular hydrogen so important?
Because H2 is a powerful geochemical source of energy. On Earth, certain types of microbes, known as methanogens, can metabolize molecular hydrogen along with dissolved carbon dioxide to gain energy, producing methane as a byproduct. This process, called methanogenesis, is thought to be one of the most ancient forms of metabolism on Earth, thriving in environments like hydrothermal vents.
So Enceladus might have microbe food readily available.
Potentially, yes, especially if the ocean is alkaline, as models suggest it might be due to a process called serpentinization, that interaction of water with certain types of rock in the core, which naturally generates heat, and that energy-rich hydrogen.
This is where it gets really, really interesting, isn't it? Enceladus is like this little cosmic ticking time bomb of potential life. And the discoveries just keep getting better, even after Cassini ended.
They absolutely do. Post-mission analysis of the Cassini data continues to yield stunning results. For example, in June 2023, scientists announced the detection of phosphates, the P, in CHNOPS within ice grains ejected in the plume.
Phosphorus. That was the missing piece, wasn't it?
It was the last of the 6 essential elements for life as we know it to be confirmed in Enceladus's ocean. Phosphorus is absolutely vital for building DNA, RNA, cell membranes, phospholipids, and energy-carrying molecules like ATP. Finding it there was huge.
Wow. So all the ingredients are confirmed.
And then, just in December 2023, further analysis revealed the presence of hydrogen cyanide, HCN, in the plumes, along with evidence for diverse redox chemistry, meaning chemical reactions involving the transfer of electrons, which are fundamental to energy metabolism.
Hydrogen cyanide.
Yes.
Isn't that poison?
To us, yes, but HCN is also a key precursor molecule for synthesizing amino acids and nucleic acids, the building blocks of proteins in DNA. Its presence, along with other organics and chemical energy sources, led one researcher to comment that the prospects for the development of life are getting better and better on Enceladus.
It really sounds like it.
Yeah.
So if life is there, how would we actually find it? What would we look for?
That's the next big challenge. Since we can't easily drill through kilometers of ice yet, the plumes offer this incredible opportunity to sample the ocean indirectly. Future missions could fly through the plumes with more advanced instruments specifically designed to detect biosignatures.
What kind of biosignatures?
We'd be looking for things like complex organic molecules that show specific patterns suggesting biological origin rather than random abiotic chemistry. For example, unusual concentrations of certain molecules that reflect biological selection processes, or perhaps detecting homochirality.
Homochirality, what's that?
Many organic molecules, like amino acids, exist in 2 mirror image forms, like your left and right hands. They're called enantiomers. Life on Earth almost exclusively uses one-handedness, left-handed amino acids, and right-handed sugars. Finding a strong preference for one-handedness over the other in Enceladus's organics would be a very strong indicator of biological processes at work.
A preference for left or right-handed molecules. Fascinating.
Another potential sign could be looking for evidence of metabolism itself. For instance, if microbes are consuming that molecular hydrogen we talked about, we might expect to see unusually low levels of hydrogen in the ocean water or the lower parts of the plume, indicating it's being used up. Looking for these kinds of subtle but specific chemical imbalances could point towards life.
So Enceladus offers this tantalizing possibility for water-based life, similar in its basic needs to Earth life. But what about Titan? With its liquid methane and ethane seas, it seems like a completely different biological ballgame. What's the potential for life there? Could life exist in liquid methane?
Titan presents a fascinating, though far more speculative scenario for what we might call weird life based on a completely different biochemistry than ours. The idea of carbon-based life somehow managing to live and reproduce in Titan's liquid hydrocarbons, methane and ethane, is considered.
Now, how likely is it?
Well, it's generally deemed highly unlikely, or at least likely to be very limited if it does exist. Given the extreme cold and the very different chemical environment, some models suggest it might only support maybe a few pounds of microbes in total across the entire moon, if that. The energy available is much lower than in water.
Still, is there any energy source life could use there?
Potentially, yes. There are energy sources available. For example, complex organic molecules are constantly being produced photochemically high in Titan's atmosphere by sunlight breaking down methane. Things like acetylene, C2H2, these molecules rain down onto the surface. Hypothetically, organisms could gain energy by reacting these photochemically produced organics, like acetylene, with atmospheric hydrogen, H2, which is also present.
So reacting atmospheric hydrogen with organics from the haze.
That's one possibility. Furthermore, while sunlight is much weaker at Titan than at Earth, about 100 times dimmer, the light levels reaching the surface are still thought to be more than adequate for photosynthesis. If some form of life there could somehow evolve a mechanism to harness it efficiently at those cryogenic temperatures and using different pigments.
Photosynthesis in methane seas. That would be wild. But the biochemical challenges must just be immense adapting to those conditions. How would life even form something like a cell membrane in liquid methane? Our membranes rely on water.
The challenges are enormous, absolutely. For one thing, the elemental limitations are severe. While you have plenty of carbon, nitrogen, and hydrogen, oxygen is very scarce on the surface, mostly locked up in water ice bedrock. This scarcity of elements might mean that if life exists, it could only lead to very simple ecosystems.
Limited building blocks.
Right, and then there's the fundamental debate about the solvent itself. water versus hydrocarbons. Water is a fantastic solvent, great for transporting substances within a cell, but it's also highly chemically reactive, which can be destructive to complex molecules.
Hydrocarbons are different.
Liquid hydrocarbons like methane and ethane are much less reactive chemically. This means complex biomolecules might be more stable over long periods. However, they are also much poorer solvents than water, making it harder to transport things. It's a trade-off.
And the cell membrane problem.
That's a huge one. Earthly cell membranes are phospholipids, which rely on the interaction between water-loving hydrophilic heads and water-fearing hydrophobic tails to self-assemble into a barrier in water. That wouldn't work in methane.
So what's the alternative?
Scientists have actually done theoretical modeling exploring possibilities. They've proposed a hypothetical type of cell membrane that could potentially function in liquid methane at cryogenic temperatures. They termed it an azotosome.
Azotosome, meaning nitrogen body.
Exactly. Instead of phospholipids, it would be composed of small organic nitrogen compounds, like acrylonitrile, C3H3N, which Cassini actually detected in Titan's atmosphere. Computer models suggest that molecules like acrylonitrile could potentially self-assemble into stable, flexible, membrane-like structures in liquid methane, exhibiting similar properties of stability and flexibility to our Earth-based cell membranes.
A hypothetical nitrogen-based cell membrane. That's a profound difference in fundamental chemistry. If we were ever to discover life that actually uses a methane solvent in azotosomes, what would that mean for our understanding of life in the universe?
Oh, it would be absolutely revolutionary. If we connect this to the bigger picture, discovering life thriving in liquid methane would be our first truly compelling indication that the universe is full of incredibly diverse and wondrous life forms, not just variations on Earth's water and carbon theme.
It would mean life isn't limited to Earth-like conditions.
Precisely. It would broaden our definition of what life is and where habitable zones might exist. It would strongly suggest that biology isn't constrained to the specific conditions found on Earth, but can adapt to wildly different environments using different chemistries. It would be a paradigm shift.
A paradigm shift, for sure.
Yeah.
But, okay, as fascinating as the potential for alien life on these moons is, let's bring it back closer to home, in a way. What about our own human journey? Can we ever visit Saturn ourselves or its moons? Is that even feasible?
The dream of human exploration reaching the outer solar system, including Saturn, is compelling, absolutely. But the challenges are truly immense, significantly greater than going to the moon or even Mars.
What are the biggest hurdles?
Well, space itself, fundamentally, is lethal without appropriate protection. You've got the vacuum, the lack of oxygen and pressure. You've got extreme temperatures, both hot and direct sunlight, and incredibly cold and shadow. And then there's the pervasive threat of radiation.
Radiation is a big one for deep space, right?
Huge. Outside the protection of Earth's magnetic field and atmosphere, astronauts are exposed to much higher levels of galactic cosmic rays, high-energy particles from distant supernovae, and potential solar particle events, bursts of radiation from the sun. But beyond just surviving the environment, the physiological effects of long-duration microgravity on the human body are profound and still not fully solved.
I've heard about the fluid shifts and bone loss, but how exactly does microgravity impact the human body on a trip that would take years, like going to Saturn?
It's quite profound and affects nearly every single system in the body. You mentioned fluid redistribution. Without gravity pulling fluids down, they shift upwards toward the head and chest. Over time, the body adapts by reducing overall fluid volume, so astronauts can lose up to 22% of their blood volume.
22%.
Which leads to problems upon return to gravity, like orthostatic intolerance, feeling dizzy or fainting when standing up. Beyond that, there's significant bone density loss, similar to accelerated osteoporosis because bones don't bear weight. And there's muscle atrophy and impaired tissue repair in both skeletal muscles and bones.
Bones and muscles weaken. What about the heart?
The cardiovascular system is significantly affected too. The heart doesn't have to work as hard to pump blood against gravity, so it can actually shrink slightly. Astronauts experience decreased heart rates, potential heart rhythm issues, dysrhythmias, and those changes in blood and plasma volume we mentioned. The immune system also takes a hit.
The immune system weakens. That sounds bad for a long trip.
It does. Astronauts show weakened immune responses, making them more vulnerable to infections. Dormant viruses, like herpes viruses, can reactivate. And there's impairment in the function of T cells, which are crucial white blood cells for fighting infections and cancer.
And what about the brain? Does microgravity affect cognition? That sounds even scarier.
It absolutely is a major area of concern and ongoing research. Microgravity appears to cause altered cell physiology and significant changes within the central nervous system. Astronauts can experience sensory motor alterations, leading to space adaptation syndrome, essentially space sickness, especially early in flight, and potentially longer-lasting issues with balance and coordination. There's also evidence suggesting possible cognitive dysfunction affecting things like concentration and problem-solving on very long missions.
And vision problems, too.
Yes, visual disturbances are surprisingly common on long flights, a condition sometimes called spaceflight-associated neuroocular syndrome, or SANS. This can include swelling of the optic nerve, changes in the shape of the eyeball, flattening at the back, and even retinal hemorrhages, likely due to the fluid shifts affecting pressure inside the skull. MRI studies have even revealed physical neuroanatomical changes in astronauts' brains after long flights.
Actual changes to the brain structure.
Things like a narrowing of the cerebrospinal fluid spaces around the brain, an upward shift of the brain itself within the skull, and even deformation of the pituitary gland. We're still working to understand the long-term implications of these changes.
Wow. That sounds like a massive list of physiological challenges to overcome before attempting a multi-year deep space trip.
And radiation is the other major threat on top of all that, with all those charged particles flying around.
Absolutely. Radiation is arguably the biggest showstopper for long-duration human missions beyond Mars right now. Space radiation, which includes those relentless high-energy galactic cosmic rays and unpredictable solar particles.
It just goes right through the ship. Much of it does, yes. It penetrates living tissue, causing damage at the cellular level. It can cause mutations in DNA, damage crucial bone marrow stem cells, which produce blood and immune cells, and cause chromosomal aberrations in lymphocytes, immune cells. This leads to an increased long-term risk of cancer, cataracts, cardiovascular disease, and potentially degenerative diseases of the central nervous system. Shielding adequately against the most energetic cosmic rays is incredibly difficult because they generate secondary radiation showers when they hit shielding material.
So more shielding isn't always better.
Not necessarily, or at least it's very heavy. You need smart shielding strategies. And finally, layered on top of all these physical hazards, there's the significant mental health burden.
The isolation.
The profound isolation and confinement of being locked in a small spacecraft for years, millions upon millions of miles from Earth, potentially unable to even see Earth as more than a star. It places a dramatic burden on the mental well-being of space travelers. Maintaining crew cohesion, motivation, and psychological health is absolutely critical.
Okay, so with all these monumental challenges, the microgravity effects, the radiation, the psychological strain, is the dream of actually colonizing the Saturnian system even remotely realistic? I saw a NASA study mentioned predicting humans could land on Jupiter's moons within a century, and maybe on Saturn, likely meaning its moons are in orbit around it, in about 130 years. So around the year 2153, that seems incredibly ambitious given everything you just described.
It is extremely ambitious, yes, but perhaps not impossible, provided we make significant technological breakthroughs to overcome these hurdles. One absolutely critical need is the development of effective artificial gravity.
Artificial gravity, like in the sci-fi movies, spinning habitat.
Exactly. Likely through large rotating habitats or spacecraft sections. This would replicate Earth-like conditions, ideally around 1 gram of gravity, to counteract most, if not all, of the severe physiological dangers of prolonged weightlessness, the bone loss, muscle atrophy, fluid shifts, etc. Without reliable artificial gravity for multi-year trips, human health is likely unsustainable.
So spinning spaceships are a must. What else?
We'd also need vastly improved, highly reliable, closed-loop life support systems. Systems that can continuously provide breathable air, purify and recycle water with near-perfect efficiency, and potentially grow a significant portion of the crew's food while meticulously maintaining the right temperature and pressure and efficiently managing and recycling all waste products. These would have to be almost perfectly self-sustaining ecosystems for years at a time, far from earthly resupply.
So we need to live in giant spinning cylinders, essentially creating mini-Earths inside. And where would they get all their resources way out there at Saturn, billions of miles from Earth? You can't ship everything.
Precisely. Long-term sustainability requires resource harvesting, or in-situ resource utilization, ISRU, living off the land, so to speak.
What resources could we use at Saturn?
Well, the rings themselves, being composed mostly of water ice along with some rock particles, could theoretically be a source for extracting materials. Water ice is incredibly valuable. It can be broken down into hydrogen and oxygen.
For breathing air and rocket fuel.
Exactly. Hydrogen for fuel, oxygen for breathing, and fuel oxidizer. While the innermost D-ring might be less useful due to its low density, it could still be valuable for harvesting fine dust and tiny particles. The denser B-ring, although harder to navigate, might even provide larger chunks for building materials, perhaps. However, mining the rings directly presents huge technical challenges due to the high orbital speeds and collision risks.
Sounds dangerous. Any easier options?
Enceladus looks much more promising for resource collection. Those water ice-ejecting geysers we talked about, they're literally spraying processed ocean water, rich in volatiles and potentially organics, directly into space.
Just fly through and collect it.
Essentially, yes. It offers a potentially much more accessible source of water ice and other volatiles, and crucially, launching materials from Enceladus's orbit or even its low-gravity surface requires significantly less fuel than launching from deep within Saturn's main rings or its powerful gravity well. So Enceladus could become a vital refueling station or water source for a Saturnian system infrastructure.
That makes a lot of sense. Leverage the moon's natural output. Smart. And what would these colonies actually look like, hypothetically, floating around Saturn? Can you paint a picture for us?
Okay, picture this for the mid-22nd century, maybe. Hypothetical future colonies in Saturn's orbit might consist of large, rotating cylinder structures, perhaps kilometers long, like O'Neill cylinders or variations thereof, slowly rotating to provide that crucial artificial gravity in the living areas.
Kilometers long.
These would need to be largely self-contained ecosystems. Inside, you'd have dedicated resource processing units for solids, liquids, and gases, converting harvested ice and maybe minerals into usable forms like water, air, fuel, and building materials. Self-sufficiency is key.
What about living space?
You'd need spacious living quarters and communal areas, perhaps with simulated natural environments, designed to support the long-term mental well-being of hundreds or thousands of residents. Recreation is important. There would likely be docking bays or parking for expedition drones and external spacecraft, essential for transportation, exploration, and maintenance throughout the vast Saturnian system.
And science.
Absolutely. State-of-the-art laboratories would be dedicated to scientific research studying Saturn, its rings, its moons, the local space environment, maybe processing samples brought back from Titan or Enceladus, perhaps even searching for signs of alien life. A central control center would monitor all colony operations, life support, traffic control, and ensure safety standards. And of course, you'd have observatories.
Observatories with an amazing view.
Can you imagine? Providing residents and maybe even future tourists with breathtaking, unparalleled views of Saturn, its rings, its moons, and the wider cosmos, it could become a destination in itself.
Wow, that's quite a vision. So the technology for living there, while advanced, sounds like it's at least conceptually within reach if we solve the artificial gravity and life support issues. But getting there, that still seems like the biggest hurdle of all. The sheer travel time alone seems prohibitive with current tech.
It absolutely is the primary bottleneck right now. Current space travel predominantly relies on chemical propulsion burning fuels and oxidizers to generate thrust. While it's been incredibly effective for getting us to the moon, Mars, and sending probes like Cassini out there,
It's just too slow for people going that far.
it's fundamentally too slow for routine human deep space travel to the outer solar system. Consider that even Cassini, a relatively lightweight unmanned probe optimized for speed and using multiple gravity assists, still took nearly 7 years to reach Saturn, and its flyby of Jupiter averaged about 4 years into the mission.
7 years one way.
And that was for a probe programmed to maintain a high flyby speed without the immense challenge of carrying human passengers, life support, and enough fuel to significantly decelerate into orbit around Saturn and potentially land and return. A human mission using chemical rockets would likely take even longer, possibly decades round trip, involving massive amounts of fuel.
Decades, that's just too long.
It's generally considered too long from a physiological, psychological, and mission risk perspective. Therefore, if humanity truly aims to land astronauts on one of Saturn's moons, or establish a presence in the Saturnian system by, say, 2153, as that one NASA-affiliated study speculated, it absolutely must prioritize the development and implementation of much faster, more efficient forms of propulsion. We need a breakthrough.
Like what? Fusion rockets. Something else.
Things like advanced nuclear thermal propulsion, nuclear electric propulsion, possibly fusion rockets down the line, or even more exotic concepts like solar sails for certain trajectories. Finding a practical alternative to chemical rockets is the essential key. That's what will truly unlock the human journey to the outer solar system, opening up these distant, fascinating worlds like Saturn and its moons for sustained exploration and, perhaps one day, eventual colonization.
What an incredible journey we've been on just talking about it. We've journeyed through Saturn's captivating history, its dynamic and stunningly complex rings, the incredible missions like Cassini that revealed its deepest secrets, and these tantalizing possibilities of life, maybe even familiar, maybe utterly alien, teeming in its system. It's truly a world of immense beauty and even greater scientific intrigue.
It really is. From Galileo's early confusion and his almost mythical musings about Saturn swallowing its children, to Huygens figuring out the rings, Cassini's intricate decade-long dance among its rings and moons, revealing oceans and plumes, and now, looking ahead to the potential for future human exploration and the profound search for alien life, our understanding of Saturn has just evolved so dramatically.
Right.
This connection between the past, the present, and the future of discovery is truly profound, isn't it? It
Yeah.
reminds us how far we've come in just a few centuries, and yet how much further we still potentially have to go in our cosmic journey of understanding.
Absolutely. So thinking about all this, what does this all mean for you listening right now? As we look to this potential future, maybe distant, maybe not that distant, with the prospect of humans actually colonizing the Saturnian system, imagine people living their lives in artificial gravity inside giant spinning habitats, sustained by resources extracted from icy moons or rings, surrounded constantly by the endless, intricate, beautiful dance of Saturn's rings.
What a view.
What new forms of art, culture, and even philosophy might emerge from such a civilization? How might our very perception of humanity, of our place in the universe, of life itself, transform when viewed not from the blue marble of Earth, but through the perpetual, mesmerizing lens of a ringed world, billions of miles from home?
That's a deep thought to end on.
It's a thought that I hope continues to expand our horizons and our appreciation for the ongoing quest to understand our place in this vast, amazing universe.